Work done by a constant force. So imagine we have a box which is being pulled by a force F. Now, instead of moving rightwards, let's say the box is moving at some other angle. Let's say it is moving along this red arrow. So this is the displacement of the object. So in such cases, how do we find out the work done? It is given by the formula work done is equal to Fs cos theta, where F stands for the force which needs to be constant throughout the motion. S is the displacement and theta is the angle between F and S. Now, it is very important for you to note that this formula is only valid under a particular condition. What is that condition? All the parameters which are there in this formula, F, S, and theta, all of them should be constant throughout the motion of the object. Otherwise, we cannot apply this formula. Now, let us take different situations in which we can find out the work done depending on the angle theta. Case 1, if I take theta as 0 degrees, which means imagine a situation where the force and displacement are parallel. So have a look. We have an object which is being pulled to the right side, but the object is also moving towards the right hand side. So in this case, we can say F and S are parallel, which means theta, which is the angle between F and S, is 0. And if theta is 0, we know the value of cos 0 is 1. So the work done will be Fs cos 0 and that will come out as F into S. That's case 1. Case number 2, we do theta is equal to 180 degrees. That means the force and the displacement are in opposite direction. So one easy example to visualize this is imagine we have a box and you throw the box upwards. Now look at this animation. Once the box goes upwards, which means displacement is upwards. But note as the box is going upwards, the force acting on it is mg, which is acting downwards. So let me repeat. If you take an object and throw it upwards, so throughout the motion of the object, mg will always act downwards. But notice the ball or the object is going upwards. So back to the animation, mg is downwards and displacement is upwards. So we can say angle is 180 degrees. And if we put in the formula, work done will come out as Fs cos 180. Cos 180 is minus 1. So we will write this as minus F into S. Now the value of force in this situation is mg, which was the weight of the object. Hence we can write down work done by the gravitational force mg is equal to minus mg into S. So these were the two cases which we considered, theta as 0 and theta as 180. Now there is a third case which is theta is equal to 90, which is extremely important. So can you visualize a situation where the force and the displacement are perpendicular to each other? So angle will be 90 degree in that case. So we do work is equal to Fs cos 90 and cos 90 will be equal to 0. That means imagine a situation where the object is moving, the force is there, but the work done is 0. How do we do that? We need to just make sure that the angle is 90 degree. Now the easiest example to visualize this is any circular motion. So for example, consider the earth which is orbiting the sun. Now think, what is the force which is acting on the earth? That is the gravitational force which is being provided by the sun. So the sun is pulling the earth towards it. That is called the gravitational force. So we draw this arrow. So the force is acting on the earth, but the direction of force is towards the center of the circle, which is the sun. And how do we figure out displacement in this case? So whenever an object is moving in any path, all we need to do is draw a tangent at that point to get the displacement. So in this point where the earth currently is, if we draw a tangent to this circular path, we will get an arrow like this. And now if you notice the direction of force is towards the center, displacement is tangential. Hence the angle between these two arrows is 90 degrees. Hence we said cos 90, so work done will be equal to 0. Now, no matter where the earth goes in this circular path, work done will always be 0. So let us imagine the earth in this orientation. So what is the direction of the force which is acting on the earth? So we know the sun is pulling the earth towards it. So the gravitational force will always be towards the sun, which is the center of the circle. And as earlier discussed, the direction of displacement is tangential. So no matter where the earth goes, the angle between the force and the displacement is always 90 degrees. So Hence, we can deduce a particular statement, and that is work done by centripetal force in circular motion is always zero. So please remember this as a rule. If we are dealing with uniform circular motion where the speed of the satellite is constant, like in this case, the Earth is moving at a constant speed. So this is called uniform circular motion. So in such situations, work done by centripetal force is always zero. Next, it is important for us to discuss the sign of the work done. We already know the formula for work done, which is F into S into cos theta. Now, F is the magnitude of force. S stands for the magnitude of displacement. So, F and S anyways will be positive. So, the sign of work done will be the same as the sign of cos theta. For that, it is important for us to know the shape of a cos graph. So, how does a cos graph look like? It looks like this. So cos 0 is 1, cos 90 is 0, but it is important for us to remember the general shape of a cos graph. Now we will consider different values of theta. So let's say if the angle theta is less than 90 degrees. So we are considering this part of the graph. So less than 90 degree, you can see the graph is above the x-axis. So which means we can say cos theta is positive. Now since cos theta is positive, the work done, sign of the work done will be positive. Next, we consider theta greater than 90 degrees. So if you consider the angle theta, which is greater than 90 degrees, so over here, so here you can see the graph cos is below the x-axis. That's why we can say cos theta is negative. Now, since cos theta is negative, sign of the work done will be negative. And finally, if we take theta as 90 degree, so like discussed earlier, cos 90 is 0 and hence work done is 0. And this is how we figure out the sign of the work done. Let's try to solve a question based on that formula. So a large box is pulled to the right side by a distance of 8.5 meters by a force of 55 newtons, which is acting at 50 degrees to the horizontal. We need to find the work done by this force. So all we need to do is just apply the formula W is equal to Fs cos theta, where the value of force is 55, displacement is 8.5, and the angle is 50 degrees. So if we put all the values in, we will get the work done as 300.5 joules. Next, we have this question. An object of mass m on a string moves in a circle of radius r but at a constant speed. Which of the following statements are true about the motion? Statement 1. The resultant work done on the object is 0. This is obviously true since we just discussed that in case of circular motion with a uniform speed, so a uniform circular motion, in such cases, the work done is always 0. And why is that? Because the direction of force, which is centripetal force, that is always perpendicular to the displacement. So let's draw. If I draw an arrow coming towards the center, so this is the direction of centripetal force. And to determine the direction of displacement, all we need to do is draw a tangent at the circle. So the angle between the force and the displacement is 90 degree. And since the formula for work is Fs cos theta, and in this case theta is 90, so cos 90 will be 0. So definitely work done is equal to 0. Hence statement 1 is definitely correct. Second, the velocity of the object is constant. Now this is wrong. So although the question it is saying that the speed is constant, but velocity is not constant. And why is that? Because velocity, if you remember, is not a scalar quantity. It is a vector quantity, which means direction is very important for velocity. So when an object is moving in a circular path, the direction of the velocity is constantly changing. So how do we show that? So let me draw different positions of the object. Let's say position A, then we have position B and position C. All we need to do is just draw a tangent at various points. So at point A, if I draw a tangent, so this will be the direction of velocity at A. Then at B, the direction will be like this. And at C, if I draw a tangent, this is the velocity at C. So now you can say that even though the speed is constant, speed is nothing but the magnitude of velocity. So although the speed is constant, but the direction of velocity is constantly changing. Hence, velocity of the object is not constant, it is changing. So the statement 2 is wrong. Then the third statement, the object is accelerating. This is also correct. And how can we say that? Because if you try to recall the basic formula for acceleration, acceleration is change in velocity upon time. Now, since we have already deduced that velocity is not constant, which means delta v is not zero. Hence, the value of acceleration is also not zero. Hence, statement 3 is correct. The object